Hello, everyone. My name is Rocco Rinaldo, and today I'll be presenting SyzTrust, a state-aware fuzzing framework designed specifically for trusted operating systems on IoT devices. This work was first published at IEEE Security and Privacy Conference 2024 and represents a collaboration between researchers at Zhejiang University, EPFL, UCLA, and Georgia Tech. The key contribution of this work is SyzTrust, the first automated fuzzing system capable of testing closed-source trusted OSs on resource-constrained IoT hardware. Here's what we'll cover today. I'll start with some background on trusted execution environments, or TEE, and why their security matters. Then we'll discuss the two main challenges that make fuzzing IoT trusted OSs difficult. After that, I'll walk through the SyzTrust design and architecture, followed by evaluation results showing 70 vulnerabilities discovered across three major vendors. We'll wrap up with security insights and lessons learned. Let's start with what a trusted execution environment actually is. A TEE for short is essentially a secure enclave, a protected area on the main processor that's isolated from the regular operating system. Its job is to ensure confidentiality and integrity of sensitive code and data. Think of it as a vault inside your processor where secrets like encryption keys are handled. A TEE has three main components. Client applications, or CAs, run in the normal world. These are your regular apps. And then trusted applications, or TAs, run in the secure world. These handle sensitive operations. The trusted OS is the foundation that enables all security functions. The trusted OS is what the researchers targeted because if it's compromised, the entire security model collapses. And to give you a sense of the scale of the attack surface, Global Platform reports a 25% year-over-year increase in TEE-enabled IoT processors being shipped. Look at the specific technology at play here, and that's ARM TrustZone M. TrustZone for ARM v8-M was introduced in 2016, specifically for Cortex M23 and M33 microcontrollers. Unlike TrustZone for Cortex-A processors and smartphones, this version is optimized for IoT. It has faster context switching between worlds. It's designed for low power, battery operated devices, uses memory-based world division rather than a separate secure monitor. And as you can see in the diagram, the processor is divided into a normal world and a secure world. The normal world runs your regular applications and a rich OS like FreeRTOS. The secure world runs trusted applications and the trusted OS with the TEE internal API. By now, you might be asking yourself why trusted OS security matters. Why should we care about trusted OS security? When a trusted OS is compromised, the consequences are severe, and this is why. Sensitive information leakage, and we've seen this with CVE 2019-25052. Arbitrary code execution within the trusted context. Attackers can create backdoors in the Linux kernel itself. Real world examples. Researchers extracted full disk encryption keys from Android's Keymaster service. These trusted OSs are deployed in critical devices. Unmanned aerial vehicles like drones, smart locks protecting physical access, industrial control systems. The challenge was that manual reverse engineering didn't scale. There are too many different MCUs and too many vendors. There was need for automated security testing. Let's define the threat model the researchers considered. The attacker has three main goals: gain control over other trusted applications or the trusted OS itself, extract confidential information like encryption keys, cause crashes leading to denial of service, and consider two realistic attack scenarios. Scenario one, a malicious client application passes carefully crafted data to a trusted application. For example, this would be CVE 2022-38511, and it was triggered simply by passing a large key size value from a client application to a trusted application. This is practical because anyone can write a normal world application. Now, scenario two, injecting a malicious trusted application into the secure world. This could happen through rollback attacks or hardware fault injection. CVE 2022-47549 demonstrated this is feasible. Now let's dive into the first major challenge the researchers faced: the inability to instrument code and the restricted execution environment. Challenge one has two parts. First, trusted OSs are closed sourced and often encrypted. Vendors like Samsung and Alibaba don't release source code, and many trusted execution environments implementations are encrypted before deployment. This means the researchers could not instrument the code to track execution because traditionally coverage guided fuzzing relies on instrumentation. Second, IoT devices are severely resource constrained. We're talking about microcontrollers with limited memory and processing power. Binary instrumentation techniques are too heavyweight. They'd slow execution to a crawl. The alternative, rehosting in an emulator, that has its own problems. IoT devices are highly hardware dependent. And the other problem was accurately emulating the hardware behavior is very difficult. The only existing trusted execution environment rehosting solution, Part-Imu, isn't publicly available and doesn't support Cortex-M. So researchers couldn't instrument and couldn't emulate, so a different approach was needed. The second challenge the researchers faced was that trusted OSs are complex and stateful. Challenge number two, the statefulness problem. Trusted OSs are surprisingly complex. They implement multiple cryptographic algorithms, AES, MAC, for example, and unlike Cortex A processors, Cortex M MCUs don't have hardware crypto acceleration. So the trusted OS implements these algorithms in software and maintains state diagrams to track execution context. Here's why this is a problem for fuzzing. To explore deep functionality, you need specific syscall sequences in specific orders. You need the right combination of state-related arguments. But there are no response codes informing you what state you're in. Without state awareness, a coverage-based fuzzer will miss deep states and vulnerabilities. Here's a concrete example. Setting up an AES encryption and a MAC encryption might execute the same code paths initially. A coverage-based fuzzer sees no new coverage and discards one of them, but they lead to different internal states with different vulnerabilities possibly. Existing state inference methods either need protocol response codes or source code access. Neither were available. So how did the researchers solve these challenges? Let me introduce SyzTrust, a hardware-assisted state-aware fuzzing framework. SyzTrust architecture overview. SyzTrust uses a two-module design to address the resource constraint issue. The fuzzing engine runs on a PC. This handles all the heavy lifting. Test case generation and mutation, seed selection and corpus management, trace collection and coverage calculation, state variable monitoring. The execution engine runs on the actual MCU. It's just a lightweight proxy, a CA/TA client app trusted app pair. It receives test cases and executes them on the real trusted OS. These two components are connected via a debug probe, specifically a Seeger JTrace Pro. The workflow is straightforward. Generate test cases on the PC, send them to the MCU via the debug probe, execute on the real trusted OS, collect ETM traces for coverage, monitor state variables, calculate composite feedback, use feedback to guide the next iteration. This approach fuzzes the actual trusted OS without any modification. Let's talk about SyzTrust inputs. SyzTrust takes two types of inputs: syscall templates that define the structure of valid inputs. They're written in Syslang, that's syscaller's description language. They define syscalls with their argument types and uses resources to express data dependencies between syscalls. Researchers extended this with helper syscalls to handle complex structures in total. They created 37 syscall templates covering all standard GP trusted execution environment crypto APIs, plus they created 8 helper syscalls. Initial seeds is the other input, and they provide valid starting points. These are syscall sequences that actually work. Constructing them manually, though, is tedious. crypto operations have specific constraints. The solution? Researchers derive seeds from OPTEE's test suite. And what that is an open source, trusted execution environment for Cortex A processors. The researchers automatically injected logging, converting logs to seeds, and added dependency annotations. This preparation is a one-time effort that enables testing across multiple trusted OSs. Let me explain some of the key design decisions the researchers made for the hardware-assisted framework. First, the researchers decoupled the execution engine from the fuzzing engine. All heavy computation happens on the PC: seed management, mutation, coverage analysis. Only lightweight execution happens on the actual MCU. This respects the resource constraints of IoT devices. Second, they used a debug probe as the bridge. The Seeger JTrace Pro uses ARM's DAP or debug access port. It can directly read and write to the MCU's memory, writing test cases to a specific memory location. The client application on the MCU watches for new payloads. Third, researchers designed a proxy client application trusted application pair. The client application monitors memory for incoming payloads. The trusted application deserializes the payload and invokes syscalls on the trusted OS. This lets the researchers test the trusted OS without modifying it. Now you might be asking yourself, how do you get coverage feedback without instrumentation? Well, the researchers leveraged ARM's embedded trace macro cell, or ETM for short. ETM is a hardware feature that non-invasively monitors execution. Think of it like Intel PT or process trace for ARM. It records which instructions were executed, but raw ETM output has problems. First off, it's noisy. ETM records everything on the MCU, not just the executions on the trusted OS. The researcher solution was to use event-based filtering. They set up data watch points to start tracing when a syscall began and stop it when it ends. They also filter by address range to only include the secure world execution. Secondly, they needed coverage metrics, not just raw traces. Decoding traces to instructions is expensive. So instead, they calculated coverage directly on raw trace packets. They use LCSAJ, linear code sequence, and jump basic blocks. Hash operations transform these into coverage IDs. This gives the researchers branch coverage feedback without any code modification. State variable inference. The state-aware component is what makes SyzTrust unique. From the global platform specification, we know that trusted OSs maintain two key structures. The TEE operation handle, this stores cryptographic operation context, and the TEE object handle, this stores key and object context. Variables inside these structures control execution flow, things like algorithm type, operation mode, current state. The challenge was that these structures are closed source and customized per vendor. So the researchers used the inference method that works as follows. First, run a 24-hour baseline fuzzing session. Collect the contents of both handles after each syscall. Parse it into 4-byte sequences. Filter out randomly changing values. These are the pointers, the keys, ciphertext. Keep values that occur consistently but change with specific syscalls. These are your state variables. Researchers achieved an 83.3% average precision across all tested trusted OSs. They identified variables including algorithm, operation class, mode, and handle state. You might be asking why both code and state coverage are needed. The reason? Pure coverage-based fuzzing has a blind spot. For example, different crypto configurations can execute the same code pass initially, and a coverage-based fuzzer sees no new coverage and discards potentially interesting inputs. But those inputs could lead to different states and possibly different vulnerabilities. SyzTrust uses two data structures. HitMap, this tracks how often each state is visited. Map state hash to hit count. SeedMap stores seeds that reach each state and maps state hash to a bucket of seeds. Each seed includes its syscall sequence and branch coverage. Seeds are preserved that trigger new states or new code coverage. This ensures the fuzzer explores both breadth of code and depth of states. Given the seed corpus, how did the researchers select seeds for mutation? They used weighted random selection with 2 steps. Step 1, select a state. Prioritize rarely visited states. Weight equals 1 divided by hit times. So a state visited 10 times is 10 times less likely to be selected than one visited once. This pushes exploration toward unexplored states. Step 2, select a seed from that state's bucket. Prioritize seeds with high branch coverage. Probability is proportional to coverage. High coverage seeds are more likely to reach interesting code when mutated. Both probabilities update dynamically during fuzzing. This balances exploring new states while maximizing code coverage. Now for the evaluation. Let's take a look at how SyzTrust performs in practice. SyzTrust was evaluated on 3 real-world trusted OSs from major IoT vendors. M-Tower from Samsung follows the global platform specification. Tiny TEE from T-Sing Link Cloud, also GP compliant, serves 30 plus downstream manufacturers, including Panasonic. Link TEE Air from Alibaba Cloud, a proprietary implementation. This mix tests both standards compliant and proprietary systems. The hardware setup. A Nuvoton M2351 development board with Cortex M23. A Sager J-Trace Pro debug probe. A standard PC running the fuzzing engine. And then the research tracked 3 metrics. Branch coverage to assess code exploration. State coverage to assess depth of state exploration. And unique vulnerabilities found. Research question 1. What's the performance overhead? Researchers measured time spent in each phase. The reset, 256 milliseconds to reset the MCU. Transfer, just 5 milliseconds to send test cases. Execution time, 5,834 milliseconds. Coverage calculation, 195 milliseconds. Total, about 6.3 seconds per test case. Execution takes 93% of the time because test cases average 14.4 syscalls each. Crypto operations are computationally expensive on MCUs. The reset overhead is acceptable and actually helps. Clean state after each test case, eliminates false positive coverage. ETM tracing was found to be efficient. Peak throughput, 168 kilobytes a second. 92% of trace files are under 2 kilobytes. Tracing takes less time than syscall execution. Research question 2. How effective is SyzTrust? Researchers compared SyzTrust against SysCaller, the state-of-the-art kernel fuzzer, and baseline SysCaller for over 48 hours on M-Tower and compared the results. The numbers speak for themselves. Code coverage saw a 66% improvement. SysCaller 1,191 branches. SyzTrust 1,983 branches. State coverage saw a 651% improvement. SysCaller 284 states. SyzTrust 2,132 states. This is a 7.5 times increase in states explored. Vulnerability detection saw a 31% improvement. SysCaller, 26 unique vulnerabilities found. SyzTrust, 35 unique vulnerabilities found. The key insight, SyzTrust found 8 vulnerabilities that SysCaller completely missed. All 8 were in deep states, requiring syscall sequences longer than 10 calls. SysCaller discarded these sequences because they didn't contribute new code coverage. The state-aware approach preserved and explored them. Research question 3. How accurate is the custom state variable inference? Researchers validated inferred variables against actual usage in the code. For M-Tower, They saw a 87.5% precision. 24 variables inferred, 3 false positives. For tiny TEE, 82.6% precision. 23 variables inferred, 4 false positives. For link TEE air, 71.4% precision, lower because it's proprietary with different structures. 14 variables inferred, 4 false positives. Researchers validated state variables including algorithms, which crypto algorithm is configured, operation class, cipher, MAC, digest, mode, encrypt, decrypt, sign, verify, handle state, whether operation is initialized. False positives were mostly length indicators for buffers. These have minimal impact on fuzzing effectiveness. Research question 4. How vulnerable are real-world trusted OSs? SyzTrust ran for 90 hours on each target. The results: M-Tower from Samsung had 38 unique bugs. Tiny TEE from T-Sing Link Cloud, 13 unique bugs. Link TEE Air from Alibaba, 19 unique bugs. Total, 70 previously unknown vulnerabilities. Of these, 28 have been confirmed by vendors. At the time of writing of the paper, 10 CVEs had been assigned so far. The vulnerability categories follow CWE classifications. Null untrusted pointer dereference was the most frequent. Trusted OSs didn't validate input pointers from trusted applications. Buffer allocations without limits allows denial of service through memory exhaustion. Buffer overflows. Missing bounds checks on length parameters. All vulnerabilities had been responsibly disclosed. Let me walk through 2 specific vulnerabilities the researchers discovered. CVE 2022-35858, stack-based buffer overflow, CVSS 7.8 high. The location was in TEE populate transient object function in M-Tower. The bug creates a local array using the ATR pointer parameter without checking its size. Exploitation: pass a large attribute count value. Impact: denial of service, information leakage, or arbitrary code execution. This is a classic buffer overflow, surprising to find in security critical code. CVE 2022-40759, null pointer dereference, CVSS 7.5 high. Location was in TEE MAC compare final function in M-Tower. The bug accepts null for the operation parameter without validation. This vulnerability is special. It requires reaching a specific state first. You need to configure a MAC operation, set the key, and initialize it, and only then does calling MAC compare final with null trigger the crash. A traditional fuzzer would never have found this. It requires state awareness. The key insight box emphasizes 8 vulnerabilities were only found by SyzTrust because they require deep states that coverage-based fuzzers would have discarded. What does the security community learn from the researchers finding 70 vulnerabilities? Lesson 1. Similar vulnerabilities to OPTEE. M-Tower and Tiny TEE share vulnerable implementations with OPTEE. Functions like TEE malloc and TEE realoc allow unlimited allocation. On a resource-constrained MCU, this easily causes denial of service. Security principles designed for Cortex-A don't translate to Cortex-M. Lesson 2. Input validation deficiencies. Pointers and critical parameters consistently lack proper validation. When a trusted application passes a malformed pointer, the trusted OS crashes. Researchers' recommendation: add a handler list to track whether handles are allocated or freed. Don't just check if a pointer is non-null, verify it's a valid allocated handle. Lesson 3. Missing security mechanisms. Critical syscalls are implemented in non-privileged code. This means a malicious trusted application has direct access to vulnerable functions, and some would even say worse, no ASLR. Everything loads at fixed addresses. Combined, these make exploitation much easier. The constraint: security mechanisms add overhead that IoT devices may not be able to afford. This is a fundamental tension in IoT security. The researchers were transparent about limitations and discussed future work. Current scope primarily targets the global platform TEE internal core API. Proprietary trusted OSs require additional configuration. The researchers demonstrated this works with Link TEE Air, but it's not automatic. Some assumptions. A trusted application can be installed on the trusted OS, and that's needed for the proxy approach. ETM must be enabled on the debug interface. Some trusted OSs in tight supply chains may not allow either. For those, researchers suggested needing vendor collaboration. The scope of testing. Researchers focused on the trusted OS itself. Trusted applications and peripheral interactions were not covered. Future directions researchers would like to see extend to Cortex-A trusted execution environment OSs like OP, TEE, and Hawaii's iTrustE. Add trusted application fuzzing capabilities. Test interactions between peripherals and the trusted OS. SyzTrust is the first automated fuzzing system for IoT trusted OSs. Key contributions of this work are a hardware-assisted framework using ETM for non-invasive coverage collection, novel state variable inference that works on closed-sourced binaries, a composite feedback mechanism that combines code and state coverage. The results demonstrate clear effectiveness. 70 previously unknown vulnerabilities across 3 major vendors, 10 CVEs assigned for Samsung, T-Sync Cloud, and Alibaba Cloud, 66% higher code coverage than the baseline, 651% higher state coverage, 31% more vulnerabilities found. The tool is open source and available at github.com/SyzTrust. This research provides a security community with a powerful tool to improve trusted execution environment security in IoT devices. Again, thank you for your attention. The paper is called SyzTrust State-Aware Fuzzing on Trusted OSs Designed for IoT Devices from IEEE SMP 2024 conference. The code is available at github.com/SyzTrust, and I'm happy to take any questions on Ed. Thank you.